Okay, I can see people are still joining, but I think it's time to start. So welcome to SAZERAC, the last day of the 2021 edition. We're at session 5A today. We're going to be hearing about escape fractions, ionizing photon productions, and also 21 centimeter observations. And so just a reminder to everyone, we'll have 10-minute talks, and then you can ask questions on Slack. So go on the Slack SAZERAC 2 5A channel, and then you can see the different threads where you can post your question for each of the individual talks. And with this, without further ado, I would like to introduce Rohan Naidu, who is he's a PhD student at Harvard, and he's going to be talking about double bubble Lyman trouble. Go ahead, Rohan.
Good morning, good afternoon, good evening, everyone. My name is Rohan Naidu. I'm a final year PhD student at Harvard. Most of the work I'm going to present today is in close collaboration with Yorit Mate. And I have the immense privilege of being supervised and advised in all my endeavors by Charlie Conroy and Pascal Louis. So this talk is going to be a talk about escape fractions. Escape fractions are our single greatest hurdle to progress when it comes to understanding cosmic reionization. By escape fractions, I mean the fraction of ionizing photons that are produced in these early star-forming galaxies that then make it out of their ISM to reionize the IGM. And you can see you have very radically different reionization histories that are possible depending on what the escape fraction properties of galaxies look like. So if bright galaxies are efficient reionizers, you end up with reionization by the oligarchs. Versus if it's faint galaxies that are the most prolific producers and also escapers of ionizing photons, then you end up with something like a more democratic, smooth reionization. And progress on escape fractions has been so difficult because direct observations are impossible at higher redshifts. And even at slightly lower redshifts, things are really complicated because of the stochastic nature of the IGM. So you only have lower limits to individual sources. So what we often do is we look for indirect estimators of Lyman continuum escape. And the highest fidelity indirect tracer in recent years that has emerged is the Lyman alpha line profile. In particular, a very tight peak separation in the Lyman alpha profile seems to be a very efficient predictor of escape fractions. Another related feature in Lyman alpha profiles that you see in some of these most prolific leakers is a central component in the Lyman alpha profile. So to capture this, we introduce a new metric called the central Lyman alpha fraction, which picks up all these very extreme sources as having very high central Lyman alpha fractions. The idea is that this is basically tracing ionized channels through which the Lyman alpha can just directly escape. So putting these two indicators together, the Lyman alpha peak separation and the Lyman alpha central fraction, we are able to very efficiently pick out high escape galaxies versus low escape galaxies. And this is really powerful, right? Because Lyman alpha is very easy to measure compared to Lyman continuum. And it completely circumvents this whole IGM stochasticity problem that really hampers these high redshift studies. But what you need to access these Lyman alpha profiles is high resolution. So you need spectra that are R greater than 4,000. And you need systemic redshifts, so you know whether your central Lyman alpha is indeed central Lyman alpha. And this is precisely the data set that the X-Shooter Lyman alpha survey at Redshift 2, PI'd by Yorit, has put together. So this is really gorgeous data. I'm showing you the Lyman alpha profiles here of the entire sample. The resolution is high enough, the systemic redshifts are precise enough that you can do this business of using Lyman alpha profiles to infer things about escape fractions. I want to highlight that the sample is very well defined. It's flux limited. And because this is the gorgeous X-Shooter instrument, you get coverage all the way from Lyman alpha to H alpha. So you can do things like measure Balmer decrements and measure Lyman alpha escape fractions. So we apply these metrics to the XLS sample, and we pick out the high escape sources and the low escape sources. So about 35% of our sample has profiles like these, which don't have any flux at all at the line center, very wide peak separations, likely very low Lyman continuum escape. And about 50% of our sample has these really interesting profiles where you have a lot of Lyman alpha escaping right at the line center, very narrow peaks, so very likely to have high escape fractions. And so now what we want to do is we want to set up this very controlled kind of A/B test where we have all these low escape sources and these high escape sources. We want to stack them and study the spectral features that emerge in the median stacks. This is what the stack looks like for Lyman alpha. So of course, by design, the profile is concentrated around line center in the high escape sources. In the low escape sources, it's a much more broader profile. The peak separation is very high. I also want to emphasize that, that both these stacks have comparable stellar mass, comparable MUV, comparable beta, comparable gas phase metallicity. So the differences between them can't be attributed to these properties, at least within the dynamic range that we explored. As two sanity checks that what we are doing is really working, the stacks differ in their dust content greatly. Remember, we picked these stacks based purely on their Lyman alpha profiles. No other selections were made, and we see that they differ greatly in dust content. So this is a good sanity check that what we're doing is really working. Another really stringent sanity check comes from the Lyman alpha escape. So the Lyman alpha escape acts as an effective upper bound on what your Lyman continuum escape can be, at least near the Lyman edge. And we see that the upper bound to Lyman continuum escape in the stack is basically 10-ish%, versus here, it's more like 45%. So now we move on to other spectral features and see what the differences between these stacks are. So MG2 has attracted a lot of attention lately because it might be a very sensitive indicator of escape fractions, and it'll be accessible with JWST at very high redshifts. And indeed, we validate the immense promise of MG2. In our high escape stack, we see the MG2 is basically emitted at no velocity offset, and the doublet ratio is very consistent with a low column density. Versus in the low escape stack, we see the MG2 is really redshifted by about 130 kilometers, and the doublet ratio is consistent with having basically a high column density. Another really striking difference between both the stacks is in their O32 ratio. So the literature around O32 has been a bit muddled, right? There's been like promise, and then there's been pessimism. But what we find is a very, very clear difference between these stacks in terms of their O32. In the high escape stack, you have a factor of 3 greater O32 compared to the low escape stack. The log U, which is the ionization parameter implied by this very high O32, is comparable only with the superstar clusters as a population, as per Lisa Cooley's amazing review. The feature I'm the most excited about, though, is the extraordinary stellar hardness that we see in the high escape stack. So we see nebular carbon-4 and nebular helium-2 in the median stack. So I want to really emphasize that this is the median stack. It's not just 1 or 2 random oddball galaxies that are emitting helium-2. This is more than a dozen galaxies, and we are seeing these really hard lines in the median stack. The low escape sources have no signs of these very hard lines. And what this is telling us is the high escape stack must really be powered by the most massive stars, very young, order of 10 megayear populations, produced in very fresh starbursts, providing an empirical link to all the talks we heard about burstiness being linked to Lyman continuum escape and all the work from simulations that has been suggesting that picture. The other reason these really hard photons are a total game changer is because they escape really easily. So what I'm showing you on the left here is an SED that is matched to our stack's properties. So you see a lot of helium-2 flux. And what I'd like to draw your attention to is the Lyman continuum transmission. So at the Lyman edge, you might be measuring an escape fraction of about 40%. But for these very hard photons, the escape fractions are like 90%. Because the photoionization cross-section is just so low for these very hard photons. So accounting for this effect, totally boosts the escape fractions we are measuring close to the Lyman edge based on all these indirect indicators, like, for example, from the green P sample. So the key takeaway from this whole exercise, I would say, is we bound the Lyman edge escape fraction for our high escape stack to be between 20-ish% and 50%. So the lower limit comes from selection. So we selected them to have more than 20%. And the upper bound comes from that argument about the Lyman alpha escape fraction being a pretty stringent upper bound. And then we convert this Lyman edge escape to a total escape across the entire ionizing continuum. And that gives us these figures. So for basically half the greater than 0.2 L star LAEs at redshift 2, you get these numbers, escape fractions between 40 and 75%, and a psi ion that is among the highest recorded for any population at any redshift. Remember, the psi ion is adjusted for this escape fraction. This is eminently extrapolatable because Lyman alpha luminosity functions are remarkably stable between redshift 2.5 to 6. So the relative fractions of faint and bright sources in our stack are very comparable to those at higher redshifts. So that is one prong of the argument. The other prong of the argument is that Lyman alpha profiles that are intimately linked to Lyman continuum escape are also redshift invariant, it seems. So there's a beautiful paper from Matt Hayes recently who demonstrated that the entire evolution of Lyman alpha line profiles can be explained purely in terms of the IgM transmission. So putting these two things together, we can extrapolate and get out an emissivity from redshift 2 to 8. So you see this beautiful flat emissivity that is really difficult for reionization models to match, but it just falls out naturally from the flatness of Lyman alpha luminosity functions. And the way to think about this is the steeply falling star formation density is counterbalanced by the rising Lyman alpha fraction in the overall star forming population. And you get out this very coherent picture of how the ionizing emissivity should evolve. So in my last minute, I just want to preview two JWST programs that are also going to be placing some really interesting constraints on the ionizing properties of these EOR galaxies. So this program that I'm leading along with Yarit is focused on COLA1, which is a bubble with a very strongly constrained size. So we've heard about a lot of ionized bubbles in the Epoch of Reionization, but this is the bubble that we have a really good sense of the size for. So it's a situation that's like a Stromgren sphere. We have a sense of the size, so we can back out what the total ionizing budget is, and we can see whether it's coming from galaxies like COLA1 that are very bright or from many other fainter galaxies. I also want to emphasize that this is going to be one of the deepest NIRCam GRISM pointings in cycle 1, so it's going to be a great pathfinder for what future deep GRISM surveys can produce with JWST. The other bubble is the redshift 9 LAE that we heard about yesterday in Rebecca's talk. So it's an LAE at redshift 9. So the question is, why do we see Lyman alpha when the universe is so neutral? Our hypothesis is this is one of the first ionized overdensities where cosmic dawn broke first. And to test this, we're going to run a blind F44W GRISM survey to get O3 redshifts and H beta psi ions. I also want to highlight that this is going to overlap with Sears in about 50% of the footprint. So that's going to produce really amazing science because it's going to be like the Spitzer IRAC bands, but with GRISM. So that's going to be fun. And I'll leave my conclusions here. Thank you so much.
All right, so we probably just have time for one question. So there's a question about whether you have IFU data to study the environment of these objects, and would you expect to see a difference between the galaxies with lower high escape fractions in IFU data?
We don't have IFU data currently, but that is something we totally like to look into because the Lyman alpha emitters in general are more compact compared to the general galaxy population. So their sigma, their star formation surface density, is indeed higher. But even within Lyman alpha emitters, is there a difference in compactness? That would be really interesting to look at. And also to look at how diffuse maybe the Lyman alpha halos are. Maybe in the leakers, they're much more compact compared to the non-leakers. That is what my expectation would be.
All right, well, there's plenty more questions in the Slack for you to check out later.
Yeah, thanks a lot, Rohan. Yeah, indeed, we have to move on. So our next speaker, Rohan, if you stop sharing. Our next speaker is Haruka Kusakabe. She's a postdoc at the University of Geneva, and she's going to be talking about Lyman alpha halos.
Thanks for the introduction and organizing this wonderful conference and giving me an opportunity to introduce my work here. As a part of talks on hazy analogues, I will introduce Lyman alpha halos around UV-selected galaxies at redshift 3 to 4 as a cesium tracer. The second galactic medium, cesium, is a gas surrounding galaxies and regarded as a source for galaxy star-forming fuel. The gas is exchanged between the cesium and the ISM via inflows and outflows. The cesium has radiative transfer effects on ionizing and Lyman alpha photons, so it is important to study the cesium not only for galaxy evolution, but also for reionization. The cesium has been observed with absorption imprinted in the spectra of background pressures, such as damped Lyman alpha system and Lyman limit systems. The cesium is also observed with emission lines. However, the direct observations with 21 centimeter emission are only possible at very low redshift. At higher redshift, Lyman alpha, magnesium-2, and carbon-2 are used for tracers. These observations in emission allow us to literally take picture of the cesium. In particular, among those tracers, extended Lyman alpha emission called Lyman alpha halos have been commonly investigated. The key question in this study is, do UV-selected galaxies generally have a Lyman alpha halo? Historically, Lyman alpha halos have been studied with stacked narrow bands targeting Lyman alpha emission around Lyman alpha emitters and Lyman break galaxies in overdense region. Recently, IFUs like MUSE and KCWI make it possible to detect individual halos. So statistical property of Lyman alpha halos of Lyman alpha emitters have been studied, and now we know that Lyman alpha emitters generally have a Lyman alpha halo. However, it has been confirmed with MUSE that Lyman alpha emitters are only a small fraction of UV-selected galaxies. Therefore, we need to avoid sample biases towards bright central Lyman alpha emission, Lyman alpha emitters, and or overdense regions when we study Lyman alpha halos around galaxies. So in this work, we use MUSE data from MUSE Extremely Deep Field Survey, MXDF. The MXDF aims at the deepest MUSE air observations. Within the radius of 31 arcseconds, the integration time is from 100 to 140 hours. The MXDF is located in the XDF and overlapped with the MUSE Hubble Ultra Deep Field Survey. The data reduction is based on the MUSE pipeline with a number of specific developments and improvements. The surface brightness and the flux limits are like these values, and thanks to these unprecedented depths of MXDF, in Bagon et al. 2021, we detected the cosmic wave filament with Lyman alpha. The MXDF catalog was created by MUSE team and includes more than 600 sources. And our sample was first selected from the Rafalski HST catalog with the criterion of an apparent magnitude cut at 27.5. Out of 142 galaxies, 96% of the galaxies have a spec Z in the MXDF catalog, and UV continua of the remaining sources are detected in the MXDF data cube. Among them, 21 galaxies were confirmed to be in the redshift range of our interest, 2.9 to 4.4. 6 sources are also included in the previous MUSE halo study in Legler et al., and 15 sources are newly selected for our sample. The UV magnitude and redshift of our sample are shown in this panel. And as shown by a green rectangle, we also have a UV magnitude limited subsample with 11 galaxies. In the sample, we also have a group or pairs of galaxies at redshift 3 with very extended surrounding Lyman alpha halos. Some of the galaxies show Lyman alpha absorption and strong Lyman alpha emission. There are 2 of the LA overdensity with cosmic wave confirmed in Bagon et al. Those sources may live in different environments, therefore we calculated Lyman alpha halo fractions for all sources, including them, and only for isolated sources. To test for the existence of halos, first of all, We optimized Lyman alpha narrowbands and obtained curve of growth radius and inner radius. Next, using the main target mask and the neighboring object mask, we measure the signal to noise of the flux between the inner radius and the curve of growth radius. We tested a null hypothesis that the source does not have more extended Lyman alpha emission than the PSF convolved HST continuum-like component. We check the deviation of the surface brightness profile from that of the PSF convolved continuum at the outside of the main plate of the galaxies. Those panels show the Lyman alpha surface brightness profiles and result of the halo test for individual galaxies. All of 6 Lyman alpha halos included in Leclerc et al. Were confirmed to be significantly extended. For 15 new sources, 11 halos were confirmed. So in short, we obtained 17 Lyman alpha halos and 4 non-Lyman alpha halos. As you can see here, some of the new Lyman alpha halos show various profiles, including Lyman alpha absorption at the center and the complicated bumps on surface brightness profiles. In this diagram of UV magnitude and redshift, Lyman alpha halos are indicated by violet circles. And here, example of Lyman alpha halos. The top left object has little absorption at the center and very diffuse extended Lyman emission around it, while clear central Lyman alpha emission are seen in other sources. 4 non-Lyman alpha halos are shown here. We perform the completeness simulation for each non-Lyman alpha halo to estimate potential halo parameter sets that cannot be confirmed even with MXDF. And with these all sources, we calculated Lyman alpha halo fraction at 80%, as shown by the left gray bar. The fraction remained high even when we derived it for the UV magnitude limited subsample, shown by green bars, or even when we limited sources to isolated galaxies, shown in the middle column. Those fractions are similar to that for mu Lyman alpha emitters in Leclerc et al. And the high fractions imply that high star-forming galaxies generally have a significant amount of cool or warm cesium gas reservoir. In fact, any halo origin requires surrounding cool or warm gas. It has been expected from low G cesium observation, high G absorber observations, and simulations. At higher redshift, gas gets denser and more neutral as a result of increasing rates of coagulation and the higher mean density in the universe. So the high Lyman alpha halo fraction has been predicted, and for the first time, it has been confirmed with our UV selected sample and the MXDF data. It is also very interesting that 4 sources do not show a significant Lyman alpha halo. The top left source is a potential Lyman alpha halo with anisotropic Lyman alpha profile, like a bipolar, but the emission is too diffuse to be confirmed with circular surface brightness profiles. The top right source is the most interesting source to me. It is a strong Lyman alpha emitter with a 125 angstrom equivalent width without halo. So it may imply a poor amount of the cesium gas and may help Lyman continuum to escape to IGM. The bottom 2 sources have a weak Lyman emission at the center, implies that Lyman photons get killed in the ISM and the cesium, and then the halo-inst mechanisms may not work for these objects. Next, we calculated the mean Lyman alpha surface brightness profile of Lyman alpha halos with cosmic dimming fractions. The mean profile of 17 Lyman alpha halos is 2 times brighter than the surface brightness profile of mu Lyman alpha emitters in Vysotsky et al. But this could be explained by the difference in the sample selections. We obtained a typical Lyman alpha halo size above the 1 sigma surface brightness limit at 40 physical kiloparsec. The size can be used to estimate the incidence rate of Lyman alpha halos, which allow us to connect the H1 gas observed with Lyman alpha emission and the gas observed with Lyman alpha absorption, such as DE rays and sub-DE rays. Here we assume that Lyman alpha emission traces cool or warm gas and that the Lyman alpha halo size is 40 physical kiloparsec on average. The incidence rate of Lyman alpha halos is given like this formula with the number density from a UV luminosity function and the Lyman alpha halo fraction. The incidence rate of Lyman alpha halos for UV magnitude brighter than -18, our faintest limit is 0.76. This high incidence rate implies that almost all the sky is covered with Lyman alpha emission of galaxies from redshift 3 to 4. Moreover, this value is in between the incidence rate of damped Lyman system and some damped Lyman systems. We extended this exercise to higher redshift and fainter magnitude with assumption of halo size and number density from luminosity functions. The abundance matching for DLA's incidence rate requires fainter UV magnitude at higher redshift, and the same trends are found for sub-DLA and LLS. This trend can be explained by the redshift evolution of the absorber's incidence rate and UV luminosity functions. And here is my smiley slide. Thanks for listening.
All right, thank you very much. We'll wait just a little bit while people write their questions. All right, so we have our first question about the Lyman alpha halo galaxies you've looked at. Are they associated with clusters or groups?
So not always associated with cluster or groups. As introduced in Bacon et al. 2021, in the MXDF field, there are several LA over density, but it's not like a proto-cluster level. It's like a group of Lyman emitters. And we found a high Lyman halo fraction for those sources. But we also found a high halo fraction for isolated galaxies. So not always associated with massive structures.
Okay, thanks a lot, Haruka. There's another question and about the typical scale length of the halos that you find.
Scale length, a good question. I measured it, but I don't remember the typical value now. And it is a bit larger than or similar to LAEs in Florian studies. It was not a crazy value. And I can give the value later after the talk.
Yeah, exactly. You can always go to Slack. Okay, there's one more question. The question is, do you find any redshift evolution?
Nice question. I'm also interested in it. And for the moment, our sample is very limited with 21 sources. So it's very difficult to check the redshift evolution. But within our sample, at least we don't find any significant evolution. And in the future, we plan to apply our Lyman alpha halo test for photog galaxies in the Hubble ultra deep field sources and upcoming Muscatel sources. So our sample size will several hundreds, so we can check the redshift evolutions in the near future. Thank you.
Okay, great. Thanks a lot. Thanks, Haruka. Again, you can always ask more questions on Slack, and Haruka will answer them there. Then we have our next speaker coming up. That's Grace Telford. She's a postdoc at Rutgers and is going to be talking about extremely metal-poor O-stars in nearby galaxies, analogues of ionizing photon producers in the early universe.
Right, hello. Thank you very much for the opportunity to speak today and for all of the effort that's gone into organizing this great meeting. So I'm Grace Telford. I'm a postdoc at Rutgers, and I'm going to share with you some recent results on observations of individual metal-poor stars in the nearby universe and what this can tell us about ionizing photon production in the early universe. So we've heard a lot of talks this week about upcoming JWST observations, and that motivated the need to determine the properties of high redshift galaxies and their contribution to cosmic reionization. Now, these galaxies are star forming and haven't had much time to pollute their ISM with metals. So the light that we are observing from these galaxies is dominated by metal poor massive stars. And to translate these observations into physical properties of galaxies and ionizing fluxes, we need to use stellar population synthesis models. And so this slide is just giving an overview of the many ingredients that go into these kinds of models. For this talk, I just want to focus on 2 ingredients, which are theoretical stellar evolution models, or isochrones, and template stellar spectra. And so both of these need to be validated against observations of many individual stars. And for star-forming galaxies in particular, like those we're interested in the early universe, we need observations of massive stars in the far ultraviolet. And I'll motivate that more a little later. But so at higher metallicities, we have a wealth of FUV data on massive stars in the Milky Way and in the Magellanic Clouds. And the ongoing Ulysses program is going to create a very thorough and densely sampled library of FUV spectra of massive stars in the LMC and SMC. All of this data can calibrate our stellar models down to 20% solar metallicity, but at even lower metallicities, we have very, very few observations of individual massive stars. And this leaves our stellar population synthesis models highly uncertain for the young metal poor galaxies that we're interested in understanding in the early universe. And so to motivate why we need to care about individual stars for this, I'm going to dig into 2 stellar properties that affect both stellar evolution and their spectral energy distributions. So first, we have mass loss rates. So massive stars drive winds from their surfaces by transferring momentum to metal lines in the photospheres. And there are various different theoretical prescriptions for how mass loss rates scale with stellar properties like luminosity, shown here. These models generically predict that lower metallicity stars have lower mass loss rates. And these models agree pretty well at higher metallicities, but when you start going to lower metallicities, like that of the SMC shown in this plot, different prescriptions make very different predictions for the mass loss rates we should expect to see. And it's important to get this right because mass loss rates will dictate stellar lifetimes and evolutionary pathways, but also their ionizing fluxes. So this is showing 4 theoretical stellar spectra where the difference between the orange line and the other 3 is a higher mass loss rate. And you can see that this stronger stellar wind strongly suppresses the most energetic ionizing photons from the star. And so we need far ultraviolet spectra of massive stars to probe the resonant wind sensitive lines that can help us pin down mass loss rates at these low metallicities. Stellar winds can also remove angular momentum from the surfaces of stars, causing them to spin down over their lifetimes, as shown by this blue line here. At lower metallicities, when winds become weak, this process is less efficient, and so stars are predicted to not spin down and therefore maintain higher rotation rates over their lifetimes. And again, rotation is important for determining stellar lifetimes, evolutionary pathways, and surface properties, and all of this combines to boost ionizing photon production across the range of masses of O stars and across different metallicities. So the 2 solid lines in the plot on the right show models that include rotation, and they predict higher ionizing photon production. And so we need at least moderate resolution spectra of low metallicity stars to determine whether they really are rotating faster than their higher metallicity counterparts. So I hope I have motivated the need for new observations of metal poor O stars. And that is exactly what our team has set out to do. We targeted these 3 main sequence stars in nearby metal poor dwarf galaxies, spanning 3 to 14% solar nebular oxygen abundance. And we're looking at all of these stars during their main sequence lifetimes, the longest parts of their evolution. And I want to call special attention to the star in Leo P because this is the only confirmed O star in this extremely metal-poor galaxy. And it is now the lowest metallicity O star that has been observed in the FUV. And it's the only one of our 3 targets that is powering a strong H2 region. And in fact, it's the only H2 region in that galaxy. So here are the new FUV spectra that we obtained using HST costs. I'm ordering the spectra from lowest to highest metallicity here. And if we focus on just this part of the FUV continuum where there are many iron transitions and other metal lines, you can see by eye that in the lowest metallicity star, the continuum is quite featureless. And as you go to higher metallicity, you can see these prominent, mostly iron lines. And so this is great because it's giving us an empirical constraint on the iron opacity in these stars. And that can inform the opacity of iron to ionizing photons in the extreme UV part of the spectrum. So moving now to wind sensitive lines in these FUV spectra. I'm plotting the continuum normalized spectra as a function of velocity offset from the bluer line in each of these 2 panels. The diamonds on the right just show the positions of narrow ISM absorption features that are imposed on top of these stellar lines. And so I'm showing this nitrogen 5 and carbon 4 wind line. Now, starting with the highest metallicity star at the bottom, you can see these broad blue shifted absorption troughs. These are well-developed wind profiles, and they're indicating that this star in WLN has a relatively high mass loss rate. But if you look at the lower metallicity stars, there's really nothing visible in the nitrogen 5 transition and very weak stellar wind features in carbon 4. And so consistent with theoretical expectations, the lower metallicity stars do have very weak winds. And in future work, I'll be fitting detailed atmosphere models to measure the mass loss rates and do a quantitative comparison with these theoretical prescriptions for mass loss. And so moving now to rotation, there is a very useful complex of carbon 3 lines in these FUV spectra. There's actually 6 different lines that create a very highly structured photospheric feature. And so in each of these 3 panels, I'm showing a non-rotating model spectrum as the gray line. And you can see that this non-rotating model has a much more highly structured carbon 3 feature than what's observed in the data shown in black. And so I can apply rotational broadening to the models and fit for the V sin I projected rotation that best matches the data. When I do this, I find that the 2 lower metallicity stars in the sample are both fast rotators, so 290 and 370 kilometers per second. And this is very interesting because there have not been a lot of V sin I measurements below 10% solar metallicity, and these were not selected to be fast rotators in any way. So this is strongly suggestive that we do need to be accounting for stellar rotation when modeling low metallicity stellar populations. Okay, so to put these results in context, I use SED fitting to infer the fundamental properties of these stars, especially their masses and ages or evolutionary states. And I fit models to the combined HST FUV spectra and near UV through near infrared photometry. And this is just showing an example fit to the star in Sextans A, but the takeaway here is all 3 of these stars are relatively low mass O stars. They're between 20 and 30 solar masses and on the main sequence, but not particularly young. And so to assess the quality of these SED fits, we can compare the detailed FUV line profiles in the models shown in red here with the data shown in black. And we see actually very good agreement, which is remarkable because I've used a publicly available pre-computed model grid. And so this is extremely reassuring that these theoretical stellar spectra are getting photospheric opacities right, which is great. With these stellar properties in hand, I can now construct comparison samples for each of our target stars with stars in the small Magellanic Cloud that have also been observed with HST costs. And So this is a way of controlling for all of the stellar properties that might affect the spectral appearance, except for metallicity. And so here I'm showing our lowest metallicity star in Leo P compared to its 2 SMC analogs. And you can see very clearly, particularly in the left panel, that the wind lines become much, much weaker when you go from 20% to 3% solar metallicity. So this is an empirical demonstration that the weak winds in the Leo P star are a metallicity effect. And again, it's interesting that this is the only one of our 3 stars powering an H2 region, even though it's not the most massive or most luminous. And so the weak winds may be hardening its ionizing spectrum. Okay, I think I'm close to out of time, so I will leave up my summary slide and take any questions. Thank you very much.
Thank you very much, Grace, for an interesting talk. Just wait a little bit for people to write their questions. Okay, so we have our first question about the implications of your work on the initial mass function. Have you learned anything that would require a modification to the initial mass function?
So the short answer is no. With only 3 stars, we really cannot say very much about the initial mass function. And this is, often discussed in the literature as a possible driver of extreme emission lines that people see in high redshift and low metallicity galaxies. But 3 stars is not enough. And unfortunately, in the metal poor galaxies in the nearby universe, star formation rates are quite low, and the upper IMF is not particularly densely populated. And so there are very few massive O stars known in these nearby metal poor galaxies.
Following up on this, then maybe I can quickly ask a question. So you said there are very few, but what are the prospects of extending the sample?
I mean, yeah, I think it's definitely worth an investment of observing resources to survey these galaxies and search for, more massive O stars. None are known to date, but that doesn't mean they're not hiding out there, particularly in highly extincted H2 regions, for example.
Okay. There's no other question for the moment. Oh, here we have one. Then Ko is asking, based on your results, what single stellar population models do you recommend we use to model high Z galaxies?
Well, I do think that using rotating models would be appropriate for low metallicity populations in particular. Beyond that, I don't have a favorite model necessarily, but as I showed, TLSD spectra do a good job of reproducing the photospheric opacities, and I will be checking whether that extends to other widely used model sets too.
Okay, excellent. Okay, maybe one very quick question. Oh, there's now more. Anyway, you will have more questions on Slack, but we can do one more. You might have mentioned this, but do these stars reside in ISM regions with a similar metallicity?
So the abundances that I've quoted in this talk are gas phase oxygen abundances. Again, it will require detailed atmosphere modeling to determine the iron abundances of these stars. It is possible that the iron abundances are a bit different than the oxygen, but for now, we are assuming they're similar.
Okay, thank you very much.
Thank you.
Thanks for a great talk. Then we have our next speaker, that's Grace Olivier. She's a PhD student from OSU, and she's going to be talking about a self-consistent model for the ionizing spectrum of reionization era analog galaxies. Take it away, Grace.
Yes. Thank you so much for that introduction. I'd like to thank the organizers for giving me the opportunity to talk to you today. I'm going to be talking about this work that I've been doing with Danielle Berg and John Chisholm at UT Austin, while I am starting my final year of grad school at Ohio State. So we're talking about reionization era analog galaxies in this talk. And we know from the observations of higher redshift galaxies that high redshift galaxies are probably extreme emission line galaxies. This lens galaxy has extreme helium-2 emission that does not fit with any of the rest of the stellar models that fit the rest of this galaxy. So it tells us that reionization era galaxies probably have other extreme emission lines similar to this. And these emission lines really help us by telling us what is happening in the ionizing spectrum. For example, helium-2 is ionized by photons that are 54 eV or greater, and we are calling this the very high ionization zone because it really surpasses the regular standard three-zone model of ionization zones. And there are just all of these emission lines are telling us what is physically happening in these galaxies. Since we're studying analogs, we have the option to actually look at both UV spectroscopy and optical spectroscopy, so we can study all of the lines that are available to us so we can get a better, fuller understanding of what's happening in these analogs to reionization galaxies. So the two analogs we use for this work are J104457 and J141851. They are the two highest equivalent width measurements of carbon-4 and helium-2 in the local universe. And they're very small, compact, metal-poor galaxies. As you can see, J14 here, it fits within the aperture of COS almost completely. And the COS spectra on the left give us amazing emission lines like helium-2 and carbon-4 that are just booming. You can also see that the helium-2 velocity structure is very similar to the oxygen structure, which is shown in the bottom right here. So we know that this is nebular helium-2 that we are observing, and it is the gas that we're seeing this helium-2 come from. When we take that amazing COS spectrum, we're actually able to fit the stellar populations that are driving this galaxy. So these stellar populations that dominate in the UV tell us that the ages of these galaxies, the ages of the stars in these galaxies are 1 to 10 megayears. So they are the very young stars. And the metallicity for these stellar populations is somewhere around 10% or less. So these are good analogs to the reionization era galaxies we're hoping to find. We're hoping that you see with JWST. When we take that stellar population and we plot its ionizing spectrum, we see that on the very left here is where the photons would be that you need to create helium-2. So even with the stars that we are seeing in these galaxies, it looks like we might not have enough ionizing spectrum to create the helium-2 we observe. So that's what we want to test. And to do that testing, we are going to use photoionization modeling. So photoionization modeling, we start with the most basic level of this, where we take cloudy and we put in a single age burst of star formation that we get from BPAS. When we do this, we're going to get a number of these lines from emission lines, and we're looking at these kind of complicated plots, so I'll go into depth a little bit more. On the x-axis, we have log U. Log U is a measure of the hardness of this radiation field. So high energy hard ionizing spectrums are going to be on the right, and less energetic things are going to be happening on the left. Then we have the line ratio on the y-axis, and this is allowing us to compare lines across galaxies. And we're comparing everything here to H beta. Then we can look at the models that are on these galaxies, on these plots, and they're the colorful lines in these plots. So these lines are the width from the different ages of the stellar bursts, star formation bursts that we tried. And what's most important is the different colors are metallicity, but these models are peaking on the left-hand side for these low energy, these low ionization species. And then they start to peak further into the center of the plots. And when by the time you get to high ionization lines, they're peaking on the right side of the plot, except for helium-2, which peaks nowhere on this plot. So that's not a good sign for these reproducing observations, which is what we check next. So we compare these models to the observations of other small metal poor galaxies nearby, and we can see that the top panel, the points all fall within the band of where the models can predict these line ratios to fall for anything in the top panel. So low and intermediate ionization lines are reproduced by these models. But when we get to the high ionization lines, the points start to fall off of the model prediction area. And we get to the helium-2, and the models are nowhere near these observed helium-2 line ratios. So this is telling us that a single age burst of star formation is good at reproducing the low ionization lines, but not at reproducing high ionization lines. They're under predicting those high ionization lines. So we need to level up our photoionization modeling to the next level. If we want to reproduce everything, we're going to try, instead of a single age burst of star formation, we'd rather try the stars that are actually in these galaxies. And so to do this, we take that stellar continuum fit that I showed you earlier from the UV spectrum, and we use that as the input for our photoionization modeling in Cloudy. When we do this, we're still able to reproduce the low and intermediate ionization zones, but now we can also reproduce the high ionization zones. So this black dashed line that runs through the center of these bands is telling you the observed metallicity, and you see that the observed metallicity model is very close to those points that we see that are the observed line ratios. So this is good news for the stars, except when we get to the high ionization lines, we're still not able to reproduce the helium-2 or oxygen-4 that we see in these galaxies. So even with just the stars that we observe, we're not getting enough photons to ionize helium-2. So we need to level up our modeling again. And to do this, we add a black body. So we are not physically figuring out what the mechanism is that causes the helium-2 right now. We just want to know what temperature and like contribution to the flux is needed in order to get to the photons we need for ionizing helium-2. And so still, when we add a black body, we can still produce low, intermediate, and high ionization lines, but now the band for the models is able to encompass the points for helium-2 and oxygen-4. So this problem of reproducing the very highest ionization lines is now something that we have created a black body to fix. And again, just to show you the top model here, top panels here just show you the model including only stars. And now we're able to reproduce the highest ionization lines with an additional black body. Our black body is characterized by two parameters. We have the temperature, which is mostly determined by these lower ionization lines on the left, as they have a little bit more information about what temperature is needed to create their emission lines. And then on the right, we have this additional parameter that is the contribution to the flux. And so each of these additional lines that you see on this plot are an additional 10% contribution to the flux. So this tells us how much of the total flux this black body needs to be. So when we take these two parameters, we are actually able to tell you that the ionizing spectrum for these galaxies, in order to reproduce their highest emission lines, you need to add an 80,000 Kelvin black body at 60 to 70% of the luminosity of the young stars. So this is a significant fraction that really changes the shape of your ionizing spectrum. And so these dots show you that without the addition of a black body, we have essentially no photons that are getting us helium-2, and now we have the photons available to give us helium-2 in these galaxies. And now the question really becomes, where are we missing the stellar astrophysics? We've just added a black body and we don't know what this is. So there are a number of options that have been suggested in the literature, things like low metallicity stellar atmospheres, and Grace was just talking about low metallicity stars. Our models do not really account for the very lowest metallicity stars. And so it could be that our stellar populations are just a little bit incorrect, like Grace was talking about. There's also very massive stars, stripped stars, Wolf-Rayets, things that low metallicity that have never really been seen also shocks and ultraluminous X-ray sources. A number of these things have been suggested, and then also we have upcoming X-ray data, so it helps us to know whether or not these are the options. But if you have other suggestions for what this black body could be, we would love to hear. So again, your stars are not going to reproduce the helium-2 that you see unless our models are incorrect. Instead, we need to add a black body to those stellar models in order to get us the helium-2 and other high ionization lines that we observe. So with that, I'll take all of your suggestions and any questions that you have. Thank you for your attention.
Thank you very much, Grace, for an interesting talk. Just wait a minute while people come up with and type their questions. The last one while we're waiting, just wondering where potential like weak AGN contribution could fit in to match some of these emission lines.
Definitely. So we've checked the like BPT versions that we have of these line ratios and things, and they do still look like they fall into generally star forming areas of the BPT diagram. However, it could be that there are weak AGN in these things. They are very, very small though, with stellar masses of something like 10 to the 6.5-ish of stars. So it would be a question for that. We do have X-ray data that we could look for that we could see if there's some other high energy thing in there. So we will check. So far though, it doesn't look like we have any extra sources on that galaxy, those X-ray detections.
Okay, great. Thank you. So while we were talking, now we have some good questions. So the first one is, are these young stellar populations still embedded in their birth clouds?
So that's a good question. We have a little bit of information just by the reddening to these galaxies. We don't know for sure, and it doesn't totally look like they are really embedded in their natal clouds still. We are not doing any additional modeling to account for that. We are just assuming they are in this H2 region-like structure that is not fully dense material. I think we have H1 data for these galaxies, but aren't seeing anything crazy.
Okay, thanks. There's another question. You add now this black body, and what observations do you think we could do to distinguish between all these different possibilities that you're listing here?
Yeah, that's a good question. So we have X-ray data coming up. If we could get farther into the UV than our current data actually has from COS, we could get a little bit closer to seeing that difference in the ionizing spectrum. And also there are some additional emission lines that we're looking for. Things like oxygen 6 can rule out things like a suppressed superwind and catastrophic cooling. So there are a number of emission lines that we're looking forward to getting that we don't already have that could help us eliminate some of our possibilities.
Great, I'll ask another question. What implication would this model now have for strong carbon-3 emission that we're seeing in galaxies?
So that's a good question. Our carbon-3 is a little bit of a question right now because it's not completely fit by our models at the moment. Mostly this is a question of it's not in the highest resolution spectrum that we have. The carbon, if this additional source could produce extreme carbon-3 as well, just with the high energy photons that we have. So this could relate to that emission that we're seeing elsewhere.
Okay, excellent. I think we're perfectly on time. You have more questions on Slack. Thank you, Grace.
All right, thanks.
And let's move on to the next talk. That's going to be by Josh Dillon, who is joining us from California, from Berkeley, who's going to be talking about the first upper limits from Hera on the 21 centimeter power spectrum. Take it away, Josh.
Thank you, Pascal, and thank you to the other organizers for having me. It's a pleasure to be here on this little early in the morning in California. So I'm going to be talking about HERA, the Hydrogen Epoch of Reionization Array, and our first upper limits, which are now in referee review and have received a favorable first report. So for those who haven't talked much about 21 centimeter cosmology, we're of course interested in studying reionization like everyone else here, but we're looking at it from a slightly different lens. So we're looking at the relative brightness temperature of the 21 centimeter line compared to the cosmic microwave background. And that's probing the physics of the intergalactic medium. So it's probing the overdensity of hydrogen, it's probing the spin temperature of hydrogen, which tells us about the spin temperature of the gas, the baryons in general, and of course the neutral for hydrogen. So we're learning about the reionization by directly probing the gas that is, of course, reionized. So there's been a number of experiments, and I'll mentioning just a few here, who have slowly brought down the upper limits toward the sort of roughly what we think is the theoretical level on the power spectrum of the fluctuations of this 21 centimeter signal to a variety of measurements across redshift and spatial scale. And of course, over the last better part of a decade now, as people have learned how to do these kinds of experiments. But I want to talk about HERA, the Hydrogen Epoch of Reionization Array, which I should mention is a collaboration of institutions led by Berkeley, but across the world. And so I'm presenting the work of not just myself, but a large number of people, especially some graduate students who have done some really great work on producing this first upper limit that I'll be talking about in a minute. And I should acknowledge that we're funded by the NSF and the Foundation, to whom we are quite grateful. So how do we actually measure the 21 centimeter power spectrum? And I want to go through a very rough overview of some of the steps that are involved. So the first first step, and the one I spend a lot of time personally working on, is calibration. And the challenge of 21 centimeter cosmology is that we're looking for hydrogen out here in the early universe, but between us and the Epoch of Reionization is, of course, everything else, more or less, and especially our galaxy and other galaxies that are emitting synchrotron radio foregrounds that are something like 4 or 5 orders of magnitude stronger than the signal we're looking for. And the key to separating the two is that the 21 centimeter signal is probing different redshifts are probing different parts of the universe. So we're seeing a very spectrally complicated signal compared to the synchrotron foregrounds, which are intrinsically quite smooth. And so as long as we can maintain that separability, that smoothness in the instrumental response, we can separate the two. So one of the ways in which you can lose that separability is calibration. So the visibilities, which is the radio interferometric quantity we measure, is not just what's actually on the sky here, but it's multiplied by a complex frequency-dependent gain on every individual antenna in our array, and these antennas can be quite complicated things. So we have to understand that to some extent. And the way that HERA was designed, which is this highly redundant configuration, is that we're using the same pairs of antennas, which is to say the same physical separations on the ground, which measures the same Fourier mode on the sky effectively in interferometry. And so we're using that highly redundant information to solve for all of these gains simultaneously. So just as a little bit of example of how this works, these are what we call waterfalls. So it's time on the y-axis and frequency on the x-axis. And these are all supposed to be the same physical separation on the ground. We're looking at the phase because the visibility is a complex quantity. And of course, they're not. So we'll throw away this antenna of number 50, which never worked. And then we impose this constraint that they have to be measuring the same thing. And all of a sudden, they really do look like they're measuring more or less the same thing. So that's what's letting us, for example, integrate down. So here's a single visibility a single day, and now we're adding up 18 days together, and it looks like the noise just comes down, which is great. So now we move to the second step, and that was a very quick overview, which is specifically to look at some of the systematics. So as we're integrating down, one thing that we found was that while we have these foregrounds, which are living at, we call K parallel, the Fourier modes along the line of sight around 0, there's these systematics that are dominating here at higher K, which is the region of Fourier space that we'd like to be able to see our signal. So in work led by Nick Kern, who also did a lot of the work on this power spectrum upper limit, who was a graduate student at Berkeley and now is a Papalardo fellow at MIT, he looked at how to model these systematics. So one of the ways to understand the systematics is to, instead of looking at them in Fourier space, so this is the Fourier transform of frequency as delay versus the time that we're looking at, instead to Fourier transform time as well. And now there's actually a clear separation between the kind of systematics that are living at higher K or higher delay up here turns out that they're also at what we call fringe rate 0, which is to say they're not changing in time. And so that temporal separation turns out to be quite useful for for getting rid of systematics that are a problem. So just using those techniques based on that idea, we're able to get back down to roughly the thermal noise limit everywhere except where the foregrounds are dominating, which of course, that's what we expect to have happen. So down here, these are modes we'll probably not be able to measure, but out here, this is where we have a much better chance. So next, we want to actually go and measure the power spectrum. So this is about just binning up all these different baselines, all the different times. And eventually here we have an example of one of our deepest power spectra, which is what we then use to set the upper limits and try to say what we can about the universe. So we're measuring, of course, our power spectra. We have a whole process for estimating our error bars and our window functions as one does in cosmology. But the exciting thing to me is that when we start, with our first attempt to get onto the big board, so to speak, we're down here. We have now the world's leading upper limit on the 21 centimeter power spectrum. Hopefully this will be published relatively soon or available on the archive is relatively soon since we've had already one favorable referee report. And so we will have hopefully the best published upper limit on the 21 centimeter power spectrum. But of course, we're still a ways away from the signal we're looking for. So we want to keep pushing toward that. And I'll talk a little bit about that at the end. But before we were comfortable publishing something, we wanted to also go through and do sort of an end-to-end validation of the work we've been doing. So one way to do that, of course, is to try to simulate everything that we think we're observing into the various effects that go into our measurements. So this was a work that was led by a number of folks, including I wanted to highlight a graduate student who's now at McGill, but was a junior specialist at Berkeley, Bobby Pasqua, who really led the work on simulating a lot of these different effects. And we wanted to test the most important real world effects, especially these cross-coupling that I just talked about, the thing that is separable in time, cable reflections, which is literally the signal bounces up and down these coax cables, and that can create high spectral structure of systematics, for example. And when you put it all together, these things can be quite difficult to distinguish from the EOR. So there's a lot of work that has to be done to compare what the EOR looks like in this space to all of these systematics. And what's nice, I think, is that this is really starting to look like what the real data looks like. There's a lot of clear similarities to what we're doing. So this was another work led by James Aguirre to show that we could actually validate and all of the analysis that we did on the 21 centimeter in order to get to our power spectrum upper limits. And things are looking pretty good. So here we see, for example, power spectra that are complete. This is all completely simulated data, but with the real analysis pipeline that we used. Our foregrounds are up here. Our detections of EOR are matching in the gray line here, the input power spectrum, the input 21 centimeter power spectrum, and then we have our noise dominated region. So it looks like there's a significant region of Fourier space where if the signal were substantially larger than it actually probably is, we would have been able to detect it. And we would have detected it in a relatively unbiased way. So we are able to also quantify those biases, which raise our limits a little bit. But that was a very valuable part of this whole analysis, the whole validation process, which was to build confidence that the techniques we're using to separate this very small signal from overwhelming foregrounds was actually working. And so lastly, we want to actually interpret the information that we have. So there's a large team within the collaboration who are more traditional theorists who are trying to compare our upper limits to what they say about our models. So as one particular example that I think is quite nice, one thing that we can more or less rule out, though I wouldn't say 100% rule out at this point, is that the intergalactic medium was unheated. So we believe that the intergalactic medium was heated at redshift 7.9. And probably heated by X-rays from either high mass X-ray binaries or supernova remnants. We're not able to distinguish between those models per se, and I don't think this is a big surprise to anyone that the intergalactic medium is heated at this redshift, but this is something that you can go and say something about with a 21 centimeter signal because of this term here. If it's unheated, then the T-spin is going to follow the temperature of baryons, which are adiabatically cooling since the time of the last scattering surface. And if they are so cold that they're substantially colder than the cosmic microwave background itself, then this term can be large and negative, which makes the power spectrum of this quantity large and positive, which we would have seen. So we can rule at least out that model and say something physically about the universe, which is something that is relatively new to our field since we've been slowly pushing down toward the region of interest. But we are also going through and building up the full MCMC machinery. So I don't want to dwell on any particular plot because I don't think that our limits are really changing our understanding of reionization that much at this point. But a lot of this was just practice. So this is work in an upcoming paper that's still in preparation, where we're going to go, turn the crank and go through the full analysis and really see what can we learn about the universe from these measurements, so that when we have more sensitive measurements, we'll be able to say more about the astrophysics of reionization and the cosmic dawn and the first stars and so forth. So what's next? Well, first we have 94 nights of Hera that are still waiting in the can. So here's a number of nights bin together versus, and this was the analysis we did just that I was presenting, our internal data release 2, and here's internal data release 3 that I'm personally leading the analysis of. And so that should increase our sensitivity. We'll have more fields, more parts of the sky because we're just a drift scan instrument, and of course a lot more sensitivity. So I think we'll be able to put much more sensitive limits on the power spectrum, probably by a factor of a few. And we also have some data from our phase 2 instrument, which is what we're observing with now. And there we've upgraded the feeds to observe not from 100 megahertz to 200 megahertz, which is redshift 6 to 12 roughly, but actually up to redshift something like 25, though that's going to be quite challenging. We have a much wider bandwidth. So this is the kind of sensitivity, sort of best case that we might see with, although I think we'll do a bit worse than this, and we really probably won't be able to detect a 21 centimeter signal. Here's a couple of different scenarios, including one with a very strong radio background to explain the putative edges detection at redshift 17. But with the full Hera and the full range of redshifts, we should be, if edges is true, we should be able to see it easily. And even if it's not true, there's still a lot of astrophysics to do both at the reionization redshifts and here at more cosmic dawn redshifts. So to sum up, I'll say that we, of course, have a first and world-leading upper limit on the 21 centimeter power spectrum. There's a lot of sensitivity left to go, and this is allowing us to now do theoretical interpretation. But to my mind, the most important thing is everything that came into this, the work on calibration, on validation, on the power spectrum estimation and systematics mitigation, that have been a huge collaboration effort, is really what is going to underlie future analyses and allow us to move forward in the field. So with that, I thank you guys for your attention and be happy to take some questions.
And thank you, Josh. I'll ask a brief one while we're waiting for people to type. What is the timeline for that previous plot you showed about when you could detect or rule out the edges detection?
Right, so going back a couple slides here, actually let me go back one more, which is we are still commissioning this system. And so we're still trying to understand some of the new systematics that come with building, effectively replacing almost everything. As a bit of background, Hera was built on the same site as Paper, one of the predecessor instruments, and we actually used a lot of the same components. And now we're basically replacing all of the parts that are Paper. And the only thing that's really left are these dishes, these 14-meter dishes sitting out in the middle of the desert made of PVC pipe and telephone poles and chicken wire mesh. So I think we're still a year or two away from being able to publish something that will start to impinge on what EDGES has to say. I think the data we have in the can now, given our limited access to site with COVID and the large number of antennas that are just not working, we probably won't have the sensitivity of the data in the can right now. But I think next season, our observing season is usually the southern summer, when the galaxy and the sun are down at the same time, should be plenty of sensitivity to say something about edges. And then the question is, how fast can we go from having data to writing papers? And that's always a challenge.
All right, thank you.
Okay, we have another question. These upper limits, the question is it due to insufficient instrumental sensitivity, which I guess it is, or is there a possible non-optimal calibration strategy, or can you improve that even further to push it down?
Yeah, so we started with a relatively manageable set of data. We're talking about 18 nights, but it's still hundreds of gigabytes on disk. And so just cranking through all of that we we were not necessarily looking to get the absolute most sensitivity we could out of the data we had in the measurement. And that's kind of what we're thinking with this third internal data release, which has substantially more nights. So we are mostly limited by sensitivity, but there still are a few residual systematics. We're seeing, if I go back to the power spectrum itself, actually, I'm sorry. Let me go back a few. The power spectrum itself, there are things that look like low sensitivity detections. We are not claiming that this is a detection of anything astrophysical. It's probably systematics. And some of these are, detected at a few sigma. So there will be more systematics that we'll have to continue to understand in terms of making sure that our instrument is spectrally smooth in its response, and it's not taking these 10 to the 5 times stronger foregrounds and making them look like signal.
Okay, thank you very much. I think we have to move on. You have another question on Slack as well.
Yeah, happy to answer questions on Slack.
Perfect. So thanks a lot, Josh. Then our last speaker for this session is Tony Pal, who is joining us from UCLA, I think.
That's right.
And okay.
Thanks a lot. Yeah, so again, my name is Tony Paul. I'm a PhD candidate at UCLA working with Alice Shapley. And together with my wonderful collaborators, you can see on the screen, I've been working on this project of measuring an uncontaminated measurement of the escaping Lyman continuum at redshift 3. This paper has been recently accepted to MinRAS of the same title, so please check it out if you're interested in learning more about it. So we've already got some wonderful motivation from this session about why measuring F-escape, especially in lower redshift analogs, is important. But just to give another brief overview here, we can basically model reionization by understanding the ionizing emissivity as a function of cosmic time. So to model the ionizing emissivity, we need to know rho SFR, the cosmic star formation rate density. We need to know psi ion, the ionizing photon production efficiency. And finally, we need to know F-escape, which is the actual escape fraction of ionizing radiation that's produced in these galaxies. So this is the parameter that I'm going to be focusing on in this talk that we're going to be trying to explore. So F-escape is actually pretty difficult to observe directly. So here on the top, you can see a spectrum of a Lyman break galaxy at redshift 3. And highlighted in gold here, I have the Lyman continuum region at about rest frame 900 angstroms. So this is these are photons that have enough energy to ionize hydrogen. So in order to directly constrain F-escape, we want to see the Lyman continuum directly. Unfortunately, as you can see on the bottom plot, the transmission as a function of redshift of the Lyman continuum drops off precipitously past the redshift of about 3.5 or 4. So this makes redshift 3 a great laboratory for studying Lyman continuum directly and seeing which types of galaxies are leaking ionizing radiation. Just a general overview of our current progress of observing Lyman continuum leakers at redshift 3. So one method that's been used to find Lyman continuum leakers is using narrowband imaging. So here's just an example of 4 Lyman continuum detections at redshift 3 using a narrowband filter. Unfortunately, many of these detections have later been found to be contaminated with low redshift sources. So the work that this is pulled from, or the images that this is pulled from, is Robin Bastardi's work in 2015. She actually found 15 out of 16 of the narrowband Lyman continuum detections were contaminated. So this is definitely a huge problem. So just to give a schematic of what foreground contamination looks like, if you observe a Lyman break galaxy at about redshift 3, and you see an apparent Lyman continuum signal from that galaxy, you may follow it up with higher resolution imaging and find a low redshift contaminant along or near the line of sight that's actually contributing photons that appear to be Lyman continuum photons in the rest frame of the Lyman break galaxy. So that brings me to the sample that I'm working with, which is the Keck Lyman continuum spectroscopic survey. So this is a really deep spectroscopic survey using MOSFIRE on Keck of star-forming galaxies are selected as Lyman break galaxies at redshift 3. So 124 galaxies were observed with MOSFIRE, and 15 of them actually were found to have significant what's called F900 over F1500 out. So just to explain that parameter briefly, here is a composite of these objects in the top here. And I've highlighted the blue region, which is F900, the flux density of the ionizing UV photons from this composite, as well as F1500 is the flux density of non-ionizing UV continuum. And then the out part refers to the fact that this measurement has been corrected for attenuation due to the IGM and CGM. So after taking this average F escape measurement and performing SPS models to the spectrum, we can estimate an F escape at redshift 3 of about 9% plus or minus 1%. Also was found using this sample, higher F900 over F1500 is found with greater Lyman alpha equivalent with galaxies, as well as galaxies with lower UV luminosity. So while extensive spectroscopic removal of contamination was performed for these objects, we really need follow-up with high-resolution imaging to make sure there still aren't low redshift interlopers that were missed by the spectroscopic removal. So this brings us to an HSC Cycle 25 program, of which Alice Shapley was a PI, and it follows up these KLCS Lyman continuum detections. You can see them in pink in these 5 different fields, together with our ACS and WIFC3IR pointings that we observed these galaxies for. You can also see some non-detections that came along for the ride in these pointings that we can also do this analysis for. So you'll see that we observed in 3 different filters, the V, J, and H filters. And the reason we chose these filters is because these filter sets seem to contain information about contamination. So here you can see a VJH color diagram of some subcomponents. This is from Robin Mastardi's work again. And you can see in the upper left, these subcomponents of her Lyman continuum detections that were predicted to be contaminants based on photometric redshift fitting are in the upper left of this diagram, while the confirmed redshift 3 components are on the lower right. And this is really due to where the Balmer break falls in between these filters. So you can see at redshift 3, it's going to fall approximately between the J and H filter, while at redshift about 1.5, it falls between the V and J filter. So in order to look at these objects color diagram, we first need to separate each object into subcomponents to look for those low redshift interlopers. So here's an example of one object that was separated into two segments or two subcomponents using Sourc extractor. So now that we have these 2 subcomponents, we can make comparable measurements in V, J, and H and place each subcomponent on the VJH color diagram to see if there's evidence of contamination. So now that we have this diagram, we want to understand empirically which regions of the color diagram correspond to low redshift contaminants. So for that, we use 2 redshift subsamples from 3D HST. So one you can see in blue is built from galaxies with redshifts similar to what would be a low redshift contaminant for the sample. And then in pink, we have galaxies that are similar to our actual redshift 3 spectroscopic detections. So we took these 2 redshift subsamples in VJH color space. We built probability density functions about where the galaxies fall using Gaussian kernel density estimation. So here you can see 2 detection subcomponents are solidly in this blue cloud and therefore are predicted to be low redshift based on just their VJH colors. So I just want to show the postage stamps of the 13 objects that were confirmed to be uncontaminated. So this is really an unprecedented sample of Lyman continuum detections at redshift 3 as part of a larger statistical sample of the KLCS survey that's both confirmed to be uncontaminated through this photometric method as well as spectroscopically. So now that we have this uncontaminated sample, you can see on the left, we want to remeasure some of the sample statistics from the KLCS survey. So here you can see we remeasure the sample composites or the spectral composites of the sample and reperform that IGM and CGM correction And we now measure an average F escape of about 6%, plus or minus 1%, at redshift 3. So this is actually significantly different than the 9% that was originally measured without this removal. Yeah, so to again look at the relationships between escaping ionizing radiation and composite properties, I have these plots here. So the updated composite measurements you can see in green here, as opposed to the KLCS original measurements in red. So you can see F900 over F1500 out is again a function of decreasing UV luminosity as well as increasing Lyman alpha equivalent width. Although the relationships seem to be a little bit weaker in terms of the slope of the relationships. But they're still definitely preserved despite the contamination removal. Another thing we did is we wanted to look at the ionizing emissivity predicted from these galaxies at redshift 3, so without these foreground contaminants being included in the sample. So we basically took the relationship between F900 over F1500 out and Lyman alpha equivalent width. And we took that relationship and assumed a Lyman alpha equivalent width incidence function, as well as a UV luminosity function. And combining these three things, we can estimate Lyman continuum emissivity at redshift 3 from star-forming galaxies of about 5.5 times 10 to the 24 ergs per second per hertz per megaparsec cubed. So this is approximately comparable to estimates of ionizing emissivity from quasars at redshift 3. So even at redshift 3, galaxies are definitely significantly contributing to the ionizing background. So I'll just present a few of my broad conclusions here. So we found foreground contamination. We cleaved the sample of foreground contamination and found 2 out of 15 individual Lyman continuum detections were contaminated. We remeasured that F escape of 6% and preserved the relationship between, and we still found these relationship between F900 over F1500 out, and Lyman alpha equivalent width and LEV, and also found a significant contribution from galaxies to the ionizing background at redshift 3. And I'll take any questions. Thanks so much.
Thanks so much, Tony, for an excellent talk. We'll wait just a little bit, give people some time to ask some questions. All right, so our first question is about the contamination. Rather than just removing the candidates that appear to have contaminants nearby, have you given any thought to actually trying to clean out the contamination in some way?
Yeah, that would be really cool if we could do that. Unfortunately, basically the Mossfire slit is it's essentially capturing the spectrum from the contaminant as well as the actual redshift 3 object, basically simultaneously. So really the separation of the contaminant and the actual redshift 3 object is very small. So it's really difficult to blend that in terms of when you're extracting your 1D spectrum. So yeah, it would be really cool if we could do that. Unfortunately, for the contaminants, it doesn't seem to be possible.
There's another question here. It's a two-part question. I only asked the first part. Sorry, Jared. When estimating the emissivity, do you need to extrapolate the F escape Lyman alpha equivalent with relation? And if so, how do you do this?
Yeah, that's a great question. Yeah, so basically we assume, so we do a couple things. We assume that, we assume the Lyman alpha, the F escape Lyman alpha equivalent width relation continues out to about 55 angstroms in Lyman alpha equivalent width. And then we assume that starts to decrease, basically because the correlations between the source function of Lyman alpha and the Lyman continuum, as well as the basically that effect starts to come into play. So we model it that way, and we also we explicitly model this relationship you can see on the screen, F900 over F1500 out versus Lyman alpha equivalent width. And we also include the F escape versus Lyman alpha equivalent width together. So we kind of parameterize those two together to get a better estimate of how that relationship changes. And then, yeah, we do extrapolate or assume some sort of function or some sort of behavior past about 55 angstroms.
Okay, maybe one very quick last question. Did you also try to measure the ionizing contribution separately for low and high luminosity sources?
Yes, we did. So this is so in our paper we have both those measurements performed. So this is essentially the Lyman alpha weighted solution to the ionizing emissivity, but we also did a weight with UV luminosity. So you can essentially see in that calculation that the brighter galaxies contribute very little to the ionizing emissivity, while it's really dependent on the calculation from the dimmer sources. So yeah, that we definitely also performed that calculation. But the number itself is actually pretty similar to the Lyman alpha equivalent with weighted solution.
Okay, excellent. Yeah, I think there's more questions that you can go and answer in Slack, Tony. Thanks a lot for your talk. Thanks a lot for all the speakers in this first session of today. We have now a 45-minute coffee break. I don't know, Steve, is there any other announcements?
Not right now. Yeah, we'll start again in 45 minutes, and feel free to hang out and chat in the Wonder Me room.
All right. Thanks, everyone.